Alright, hello everyone, and welcome to today's live stream, where I actually got the thing working this time. As we can see right here, I have the geometry node bone or armature set up, and it's actually having physics, and they're working well. Quick disclaimer, because a few people were confused. This is absolutely not a real armature. This is created in geometry nodes, so it's running off of all of that, which means that it cannot be used with a regular armature node, but, the armature modifier. But I'm making my own setup that cannot work due to some limitations in geometry. It can't fully work, but it kinda works. Just through some limitations with how named attributes are gotten, and I don't think I can do all that because I can't name the bones and all that fun stuff. But, yes, it is now working, and I am very happy about that, even though it has a little ways to go before it's perfect. But for now, I can rest easy, because I've worked on this way too much. It turns out the answer was pretty simple, so let's go into that. So, for the setup in this case... Oh yeah, I should show this off. So in this case, we just have a bunch of edges that connect to a center point that is defined with a group right here, just an assignment, and that assignment is the root bone. So after that's created, and this can be applied, I'm just doing that so that I can change the rig on the fly. But once that setup of edges is done, we can go and put it into this system where we set up the rig. So in here, we basically store the parent ID, so each bone has a parent. We use the shortest edge paths node to store both the parent ID and then the chain index. Basically, the root would be 0, and then the next one would be 1, 2, 3, 4, 5, so that we can accurately see how many bones there are in the current chain. And then we store the transforms. So in this case, we get the bone transform, which is the length of, kind of the length of the edge. In this case, all the bones, their real positions, are the endpoints, because when the things join into one segment, when they actually branch, this can't work. So in this case, we get the endpoints, and then we set the position to be there in the transform. So in this case, the position is the parent index, because even though the real position is at the end, it needs to be in the previous one for the branching. And then for the orientation, we just set that with that, and then the scale, that part's easy. And then, yes, and then we go and put this into here, ignoring the root bone. That one should be unaffected by pretty much everything we do. Okay, and then we store the rest transform. Basically, we store that so that any changes that happen after the fact, we can undo and then actually apply this to a skinned mesh, which we'll get into later. And then with this version, we go and get the parent ID, and, oh wait, I should probably make it so that, that's fine for now. With this, we undo the global transforms to get the transform local to the parent, as we can see here. Simple stuff, all that's good. So that's the setup for the rig. Now there are just a ton of bones with transforms. So in this case, if I were to hook this up into our visualizer right here, which shows us the actual data, we instance the bone shape, and then this part is not really needed, but that's just to hide the root bone if needed. And then we set the instance transform to be the bone transform. So in this case, we can see that the bones do show up in their proper transforms, and that works out well. And then, after this is where we get into the simulation stage. So this part is just, actually, I could remove that, but that, oh wait, that does the pre-baking. Okay. So this basically sets the first frame of the animation so that we don't have to worry about it jumping on the first frame. So that's that. And then we go and store the Z position, which is the forward position. Basically, that's where we store the start point to the end point. So in this case, the Z position would be at the end right here. And that'll be used for the physics. So that's what we do before the simulation stage. So let's go and bring all this back into here. So here's the simulation, and here's the actual delaying parts. If you're wondering what's happening here, I just separate the different columns of the matrices and then add that together. So this is the position plus the z-axis of the 3x3 rotation matrix. And then that gets put into there. Technically, the 3x3 is the rotation scale, but yeah, it's fine. So in the stage for the actual simulation, we take our position z and then we do physics on it. But we base it in, yeah, how does this work again? I did this like 5 minutes ago. let's see. Okay, so this gets the original transform as if the bone was oriented correctly, no matter where it's oriented, just as if it was completely in its original state, though local to its parent. And then we get that, and then we have that as our target vector. We compare the current position z to the one it should be at to go where it needs to be. And then we put that into the velocity, and the velocity does all that. And then here, we increment the velocity, but also constrain it using this right here. So it'll always be the correct distance away from the parent bone. Yes, I think that is correct. And then in here is the somewhat magical part where we just go and stack up all the bone transforms from using the chain ID. It goes through, it does all that. And I forgot to label all this. I really should do that. And it just goes and stacks up all the bone transforms, which works very, very well. And then also we set the root bone to have the this transform, the transform of the empty, so that actually gets parented. And then over here is the physics. This basically says, hey, align the z-axis to the position z. Now I've tried doing this more accurate ways where I tried to separate the columns of the matrix and then doing physics on those and then putting them in there, but those didn't work, which was very frustrating. So I went with the dumb method, and the dumb method worked, which I am genuinely surprised by. So that's that, and a few other things. So I've put both of this entire section into the chain bone loop, and it did work. This is just where we go through the chain and update the roots, and then the parents first, and then it goes on to the children, and so on and so forth. And that did work, but it was slightly different, and I liked the results that I got with the other version, so we're sticking with that. This part right here just takes a vertex group, which I called freeze, and it'll basically freeze the bones if that's assigned. Which in this case, you know, adding in some customization. Again, I should mention this setup is not practical. It's an experiment to see what needs to happen before it could be practical. And the answer is quite a few things. Because right now, this remakes an entire bone armature. And all the stuff with all that. And then skinning is a whole nother pain to set up. But let me go and label these. So this is root. Yeah, set root transform. There we go. And then this one is apply physics. Yeah. And that part's fine. Yep. That one's good. Apply the physics rotations. And then set the root transform, and then that's just updating that, which we can go and put this over to here to collapse this. And that's looking very, very nice. There we go. And we don't need you anymore, and all that's working wonderfully. So if we set this to be 1, the thing will be completely physics-driven, and it won't try to go back to its original position, except where I put the freeze vertex group. And if we set it to 0, excusez-moi. Why are you... Huh. If we set this to 0, if we force it to be 0, we can see that that does up... Oh, wait, the cache didn't reset. Oh, no, that wasn't a problem with the cache. Okay, I set that up a little bit wrong. Well, if it's 0, we can see that it all freezes. So I did a little bug right there. Oh... I was a little bit dumb. Okay. Just a little bit. And why was that a switch? No. Oh, yeah, no, I screwed that up. I screwed that up. Okay, let's go and fix that real quick. So the freeze, if freeze is true, then it'll switch to something that we assign, which in this case will be 0. And then this one will be that. And then for the exists, if the freeze thing does not exist, then we will switch this to be a value of 0. Or... yeah, if it exists, that's good, and that's like that. Okay. Little fix, not too bad. There we go. And that is all good. That's fixed. Very, very nice. Yep, that seems to be correct. So now this should stay frozen, and then if we set this to be 0.5, we'll see that those parts do their job correctly. There we go. Little fix, little fix. But yeah, it actually works, and I'm so happy about it. Because I wanted to do physics on kind of bone-like structures for a while, just because it could be useful in a couple situations. Again, because we don't have access to the data with armatures and all that, having a physics-based method is good. And there's also the chance that maybe I could... Actually, okay, that would be a pain to set up, but it is possible. So, there is one way to make this actually work, where on an armature, you have a triangle per bone. And that triangle stores the transform of the bone. Or no, we could just do points. No, it has to be a triangle because you can't transfer the bone matrix onto a point. So you store all that into a triangle, and then using geometry nodes, you can go and use that triangle and then convert that into a 4x4 matrix. Do the physics on all that, and then have another armature parented to all the modified triangles. That'll do that. That's a huge pain. You should not do that. Again, this is more of an experiment rather than a practical solution, but it works. And if you're wondering why not just do this with points like a cloth simulation, well, that's because with cloth simulations, the twisting is an issue. While in this case, the normal twisting will always be aligned with the parent, which I probably should put physics on the normal axis, but I think I want to keep it simple because it short-circuited my brain a few times. My brain just completely went kaput, and I did not like that. So I did the complicated method, and then I stripped it down to just the bare essentials, and turns out it works. So I'm happy about that. And I'm scared to complicate it again. But yeah, that's that. So let's go and see the skinning version of this. So here, oh wait, I forgot to update that part. Let's start with the simple one. So here we have just a plane with the bone chain, and we can see that it's actually skinning somewhat like an armature. But the weights are procedurally generated, which is pretty cool. So let's go and take a look at that. I've been explaining this for 12 minutes, oh my god. Okay, let's go and explain this, because this one is a doozy, just because of matrix interpolations. So let's take a look at this. So in this case, we get the armature, and we put that into the, yeah, this is the plane. Then we put the armature into here, separate just the instances, because that's all fine. Set the points to be where the bone's transform actually is, rather, wait. Brain. We set the points to be where the armature's transform actually is, just to make sure that's all good. And then we set the points to be vertices, and then we turn them into edges. Again, we basically undid what we did, but in this case, it has the correct matrix data on both vertices, which I actually circumvented, but that's fine. And then we go and change that and sample that edge data on the mesh. And then this entire part is to actually do the skinning, which if you're wondering why I'm mixing the matrix, that's because mixing the transforms led to less than ideal results. So I took all the parts of the matrix, all the columns, did vector math, which is actually not as bad as mixing every single individual float. So if you do that and then transform the point, it's all good. Like, that's the only operation that's actually happening. It just sets it there and then it's all fine. So let me go through this in more detail. So here we have the rest transform and the global transform. We invert that to get the offset. So that'll say, hey, the bone moved this much between the rest and the offset. And then we get the parent transform offset, and then we make it so that the root gets ignored, which is good. And then we capture that on the point so that when it gets, when the edges happen, they get preserved. And also I just put this in here even though it's not entirely necessary. It avoids any interpolations with the matrix. It's basically saying, hey, only evaluate this data from the first one, which I could simplify this just by, we'll worry about that later. Okay. And then over here, we sample the edge index, and then we sample the edge vertice positions, which we can use to go and get the mixing data, because here we need to interpolate the matrix from the parent and the current bone. So here, let me go and turn it off. Yes, let me just skip over all this. So here we can see that the parts, when they move, they're not interpolating, they're all straight. And that's because, well, we're only getting one part of the transform and not interpolating. So when we do that, we get the parent, and that one is the original. So if we use this data to see how far along we are along the bone, so this is basically just the vector distance along the bone, and then we divide that by the length of the bone, so that it goes between a value of 0 and 1, so that we can mix this. So if we put this into here, we can see that now it interpolates, which is nice. Let me subdivide this one more time so that we can see it in all its glory. So there we go. Again, not interpolated and then interpolated, which is very nice. If you're wondering why this doesn't actually properly work as a armature, that's because we are only interpolating between the bone and its parent, instead of interpolating between all the bones that have weights, because the weights here are just automatically generated just by their distance to the bone. So that's annoying, but it is what it is. It does its job. So yeah. So that works, and then let's go and see some of the flaws with this method. So we can see on the shark, it does move and it does interpolate, even though some of the interpolation leads to bunching, which I think I have a solution for, but I'll need to go and double check on some of that. But there is a little problem with these, which is where there are branches, where there are multiple bones doing their thing, and they don't exactly... With branching like this, since it's not looking at multiple nearest bones for the weights, it's just looking at this bone and saying, oh, I'm not moving at all, that's good, but this one is moving, causing a discrepancy and causing that to happen, which is the main limitation with this one, and also because the user does not set the weights. Again, I do want this to be very procedural, so that we can, puppet things and just be able to change things willy-nilly. Originally, this was going to be made for trees, and for trees, you don't really want to make every single bone and have to weigh everything, because at that point, you just use Blender's inbuilt system. And if you want tons of trees doing a ton of different things, and they're all procedural trees, you don't want to do that. But anyway. And also, this is just a long way for getting physics in here, which, if you want to actually use physics, use the Wiggle Bones add-on. But unfortunately, with that, you cannot automate the processes all too well. Like, if you want to have wind and noise and all that, you're kind of out of luck. So I guess this is me just saying, oh, if we just, influencing bones with geometry nodes could be a very lucrative endeavor, which I did try to make an actual node for that and a modifier, and turns out I'm not good at C++, which I already knew, but yeah. In theory, it should be possible for me to make a node that just uses a sample index to sample the nearest bones, or to turn bones to edges or bones to points and all that good stuff. But, it's fine. That's fine. Let's read the chat. Looks like the geometry can make a big, high fin beta fish. Interesting. I would need to look that up. Let's see. You must have been busy with this since the stream yesterday. This is very impressive, seeing a functioning proof of concept. Well, the funny thing is, it didn't take too long after yesterday's stream. Now, yesterday's stream, I did spend way too much time, apparently, barking up the wrong tree in terms of adding physics. But after that, I went and just watched TV for an hour, and then I came back to it, and I was like, oh, wait a second, what if I just did this? I was like, this probably won't work, but let's give it a go, and then it worked. Literally the next try. So, the thing that I keep learning is if there is a problem that you keep trying to make work and it doesn't work, just leave for an hour or two and then come back, and then your mind will be clear, your eyes open, and you will see the answer in between all the math, and you won't go crazy anymore, and it'll just work. But yeah, now that it's working, it's very nice, and you can see the potential. Like, if this was an automatically generated rig for a creature, it would work out pretty well. And in this case, it would work. Like, if I had a mesh generated from all that, it would function correctly. Except where there was, tons of branching, and it's like, oh, which one's my actual parent? This one or this one? And that's why with, regular armatures, you set the bone weights, or have them automatically generated. once, and then you know, store that data, then iterate on it. But yeah, this is just a little look into what could happen with procedural bone physics and all that. Even though this is still not a great version, because it's still, there are things that I want to change with this. The main thing being that I feel like I can get rid of the Z position and just have it feed into the actual bone transform. That would probably work. Like, I could just eliminate this and then supplement it with just the, again, the actual transform. Which I could try doing now, but may be a bad idea. Well, that never stopped me before. And that would mean I could eliminate quite a few nodes. Or, well, we'll see. Okay. Yeah, sometimes I need to walk away from something that's stumping me, and it'll come to me while I'm doing the dishes or something. Yeah, just having a mental break. Because for some reason our brains just get into a rut, and you cannot free up just by doing it more and more. You need to just walk away. Which, I'm just glad this actually worked, because, you know, there's this thing called the sunk cost fallacy, which I know very well, and I keep doing it. But in this case it did work, but I just need to go away. Let's see. It's excellent. This video will be up later, I hope. Going to attempt this at some point. Yes, I would not recommend attempting it because it was painful. Well, you do have the DNA here. Go for it. If, I don't want to upload this to Gumroad just yet because I already have something else I need to upload and polish for Gumroad, and this got in the way. But you can see the nodes and you can recreate it if you want. But again, I need to stress, this is not practical. It's a proof of concept. Do not use this in production. Because it's just, it's fancy. And it could work in a few narrow circumstances. Like again, if you're just working with, if you're not trying to skin a mesh. That's the problem. Actually skinning the mesh is the issue. Simply because I can't store all of the weights. In this case, there are hundreds of bones, which I'm not, I doubt that would even be performance. I doubt that would even be performance. But anyway, have you ever created something with / about LEDs? If you mean IRL, then no. If you're meaning digitally, I did try to recreate an LED cube from a while back. It was like a 3x3 grid of colorful LEDs, and I was like, oh, I can make that in GeoNodes pretty quickly. Cooked it up in 30 minutes, and it was good. But yeah, that's the extent. I do not make a lot of stuff in the physical world, because, well, it's just quicker to do this in here, and it's more educational, if I'm being honest. Because I've learned so much math that I never wanted to, just because of necessity. So, yeah. Is it available on YouTube? It's one of the YouTube shorts. It's only the end result. I didn't show the process for it, because that was a while ago. But, yeah. That was good. It was a fun little project. Okay. And also, if you're wondering, like, oh, what if I actually needed to use, like, edit an armature, and make it use physics? Just use Houdini. Again, use Houdini or use the Wiggle Bones add-on, either or. But, yeah, this, again, is a proof of concept. Let's see. Blender absolutely makes me encounter math far more than I expected in life. Yes. With 3D programs are gigantic machines that are extremely complex. Like, behind this UI is such a complex machine, and I am amazed that it even works, given all the math that has to go on behind it. Like, have you looked inside a rigid body physics system? That stuff is painful. Like, it has to be built by a team over years. It's so complex. Like, there have been times where I'm just like, you know what, maybe I should just get into 2D animation, because you don't need to worry about any of that. You can just draw it, and you don't need to worry about physics. You just draw the physics. Pure artistic intent. But, you know, it has its perks. The issue with Houdini is that I never made my math understanding of 3D better, only Blender did. That is interesting. I think geometry nodes is, at least for my brain, easier to learn the math because, again, seeing the lines and boxes and how they relate is very good compared to looking at Vex or just coding in general. Just seeing the relations in a flow graph, which the Blender devs, even when they're coding, use flow graphs in order to see, oh, where the parts actually work together, which is very nice to see. Because sometimes, you know, if plumbing was just a series of portals with names, it would be a little bit difficult to see where the plumbing goes. So with this here, it's easier to understand. Like, again, just saying, oh, that's that, and that hooks into there, and that hooks into there. That's nice. Your brain understands it better. Which, I know people who, even though they are proficient at coding, they like to prototype things in node-based editors just because it's faster. And you could tinker with things a lot faster and see if it breaks or makes it. Alright. So anything else that I need to go over? Because that's basically the result. I don't really want to tinker with it too much here. Let me just save it here. Oh, right, the one thing that I want to try factoring out. So in this case, instead of having the Z position here, we're going to just influence the transforms, and that should be good to go. So here, instead of having the position Z, we're going to supplement it with the actual data, which means that we don't need to worry about U, and we can eliminate all that. Then inside here, we're going to supplement. There's that. Alright, and we won't have to do that either. Okay, so we can just go and take U and take you outside of the system. And yes, let's see if this will actually work. So in this case, we could add U to U. That's the actual result. And then that gets constrained. Or we don't need to constrain it. And that's good. I see that chat message. I will read it in a quick second, but I want to make sure I'm doing all this right. Transform global. Okay. So here we can supplement. Oh wait, that's the wrong one. Okay, U and then U. We can factor out U. And with U, we hook U into there. The position Z, and that's already factored out because of that. And was that the... No, that shouldn't matter either. Yep, that should be correct. And we connect U into here, even though I could just go and put U, and U into here. That's good. And then in theory, we set this to be the 4x4 matrix, which is the transform global. Connect that into there. And then instead, we put the transform global into here. Oh, wait, that's a little... That may be a bit of an issue. I did not anticipate that. We go and put U into here, U into here. Now there is... Okay, I was worried about that. Okay. Why at no work? Okay, let me read the chat message. Okay, do you have any tips on understanding vector math? Yes I do. I always love bringing this up. But the easiest way that I found out about vector math was to use the shader editor. So, get Blender up and running right now and follow the steps that I do. Or, just save this for later. So right here, if you want to see what vector math does, go and get a UV map. Right here. Here we can see that we have, in this case, it's a 2D vector, but it's fine. You can use like the position of an object. And just go and add in a vector math node and then play around with it and see what happens. So in this case, if we take the scale node, we can see that the colors get brighter. If I turned on blue, oh wait, we're in AV next, never mind. The colors are brighter, so you can see that the values increase. If we set it to be a negative, well, yeah, it goes to -1, which we can't see. If we press a subtract node, we can see that that happens. Then if we put in an absolute right here, we can see that it basically mirrors the vectors, which in this case, it's not mirroring, it's just taking the negatives and turning them into positives that we can see with our eyes. And that's that. If we turn this into a fraction node, let's go and do fraction, we can see that this makes the all this repeat. If we use the scale, we can see this multiplier or scale, they do the same thing in this case. We can see that it makes it repeat, so it takes any values greater than 1, and then it makes it repeat. If you use a minimum, we can see what this does. Whoops, here. It basically sets the maximum brightness value. Minimum and maximum are a little bit weird unless you think about them in a different kind of way. It's like choose the maximum of these values instead of, yeah, that's how that is. So here we're setting the minimum value that can exist on here, and it's only choosing the maximum out of the values. It's choosing 5.3 or anything above that. And then with normalize, here we can see that this is funky, but we can see that the brightness is all now equal to 1, just the colors can change. In this case, normalization sets the power of the vector to be 1, but the orientation of it can change. I like thinking of vectors as colors, at least that's how I learned it. Now when you go into geometry nodes, it's good to go and play around with, like, set up a vector visualizer on a point and then just see how that interacts. Or better yet, look up the Wikipedia articles. But then again, I find that playing around with it and actually getting a feel for it is better than just looking up the documentation on it. Though I would recommend that. Look at the documentation, look what Absolute actually does, Google it, Wikipedia and stuff like that. But getting a feel for it is also good. Here we can see what sine does, which in this case, it makes the wavy patterns, which you should look that up online as well. This does a sine for every vector component. I guess, like, you could also learn just the regular math nodes by doing this, just seeing how it actually affects the colors. Because again, right here, we can go, if we use a multiply and a sine, not that sine, that one can do other things. But here we can see it does the wave. And those are negative values in the black. Just assume that whenever you're seeing black values, it's either 0 or a negative. And then that's like that. And then with floor, we can see that this kind of snaps the values in increments of 1, starting at 0. And then this starts at 1 and then keeps going up. Now, since we don't have bloom enabled, we can't really see which ones get brighter in this case, but, you know, it's fine. Modulo in this case is like a repeat, but you can set the end increments. Wrap, you can see that actually wraps the values and can go into the negatives. And then snap, this is, you know, snap is like multiply, floor, and then divide. Maybe I had those flipped around. But yeah, it's basically a easier version. You know, you can just set these snapping increments, which is pretty good. And then dot product face forward. All these ones right here are a bit difficult to visualize by just colors. In that case, you need to go and actually see how they affect vectors. So again, the vector. Maybe I can go and showcase that. We have some time. And then all of these, they do what you expect. Distance here we can visualize. This will give us the distance to just a vector. But it's best to, actually, wait a second, I multiplied it by 0. Yep, that explains it. So here we can see it gives us the distance between 0.56 and 0.56 in this case. If you get the length, it'll give you the distance from 0, 0, or it'll give you the magnitude of a vector. So yeah, just going through the list, it's very, very nice. Okay. And then, yeah, these you have to visualize in order to understand that. And then tangent, we can see that this does that. Yeah, that's all fun. Tangents, tangents have been such a pain. Not those tangents, the other kind of tangents, the UV tangents. But yeah, that's how I learned. And again, look up the actual documentation. When I was learning shader vector math, I was just like, ooh, pretty colors. Let's see how the colors interact. But if you want to get down into the dirt of it, you'll need to look up the actual documentation. But getting just a general vibe for what they do, you know, seeing the colors in a fragment shader is, it's pretty good. Do you have a video, I assume you mean VOD, that explains all of geometry nodes? No, other people have done that. I would recommend that. Okay. Houdini is just a giant set of presets now, and artists don't understand its internals. People on the older days used to make better things than now because they were making some parts of Houdini from scratch. I can kind of understand it. Like, why my job, one thing I was paid for was to make things from scratch. Because there were some presets that were not doing things as expected. So it is always good to know how to make things from scratch. That's why whenever I use like an align Euler to vector node or axes to rotation node, I start to be like, oh, I should just go and make it out of the vector math nodes. And then, like the vector math nodes, you can sometimes break down into even fewer nodes, or you can break into even more nodes to show what they do. So in this case, let's go and let's get a point. Let's make a little vector visualizer here. So we'll make a point and then change it to vertices so that we can then extrude the vertices in this case. So here we should see, well, there's no vector in here, but if we use a vector and set this to be 1, we can see that we have a line pointing straight up. So that is our current vector. And now we can do stuff to this vector and see how it reacts. So in this case, if we use a scale, we can see that this gets twice as big. If we use, say, let's go and do some other cool stuff. We can try reflect, yes. So in this case, we have a reflect node, which in this case, if we have a vector that's pointing down... Wait a minute, I might have screwed this up already. Now it should be like that. Reflect, no, wait, no, yeah, that is on the Z. Okay. Oh, no, wait, it is working. What am I talking about? I'm sorry, chat, I'm a little bit cooked. So in this case, we have one vector here that's pointing down, and if we reflect it on the Z-axis, we can see that it gets reflected as if it bounced off the surface, and that's really cool. And then if we refract, well, in this case, this can act like glass, and we can see that this is also affecting the magnitude as well, which is, or... Actually, yeah, why is it doing that? I'll have to look that up. Refract, I haven't looked into all too much. Cross product. In this case, if we take two vectors, so right here we have a vector that's pointing, let's do in the positive x direction, and then another vector. If we have two of these, it's easier to visualize. And then we have one pointing in the z direction. If we cross product those two, it'll basically rotate them by 90 degrees. So in this case, we can see that plus that, or cross product that, equals a vector pointing perpendicular to both of them. Basically taking those two and then, I say rotate by 90 degrees, but it's just going in the... Sorry, everyone. I'm tired. I wanted to do a quick stream just to showcase that worked, but it's okay. Quick streams and all that. Okay. And then if we use project, now this one, I forgot what it did for a quick second. With this one, should see. Where is it? Hello? Wait, why did that... No, you should be working. Oh, wait, that's... Yeah, sorry, everyone, I'm tired. So, project, in this case. Project takes one vector and isolates, or it tells you how far along this vector is. So, again, it does what the name implies. It projects it. In this case, we can see that this one is pointing off to the side, but it only isolates the one that's aligned with the Z. And this could be any orientation. And that's because this under the hood uses a dot product, which dot products are one of the most useful functions I've been interacting with yet so far. So in this case, a dot product. This one is a little bit harder to visualize, but yeah, let's just go and do it. It'll be fine. So let's set up 3 of these and then join them together so that we can visualize all the vectors. Again, vector visualization, because we don't have just an automatic viewer for that, can be a little bit annoying, but it's okay. So in this case, we can, we'll make it so that this offset just goes up so that we can visualize it. This is getting a little bit too complicated to be practical, but oh well. Okay. In this case, oh dang. Yeah, this visualizer won't really be working too well. But dot product basically says, this one is basically isolating. It's giving you how, it's like the vector project, but just giving you the magnitude. Like, in this case, how far along is this quote-unquote z-axis along with this vector. It gives you that power. If both of these are normalized, then it'll give you a value of 1 if they're perfectly aligned, a value of 0 if they're 90 degrees off or perpendicular, and then a value of -1 if they're facing the exact opposite directions. If they're not normalized, a lot of other cool stuff can happen, which can be very useful. But yeah. I recommend looking at the actual Wikipedia pages for that, because I probably got a little bit of that wrong. But it's good to... Making a good visualizer is good for, you know, seeing how they interact. But also the names are pretty good. Like, there are some that are a little not as obvious as you would think, like dot product. You would be like, wait, what does that mean? Face forward. Yeah, read the tooltip for that one, because I forgot. Orients a vector... Oh, right. Yeah, okay, yep. That's like the... It's like... If I'm understanding this correctly... Yeah, it's like project, except it'll face forward given another vector. Okay, anyway. I looked that one up because I definitely don't understand that one yet. Haven't needed to use it. But yeah, these ones, you'll need to use a vector visualizer. The rest of them, for the most part, you can use the shader editor to get a feel for them. And that's how I learned them as a wee lad a few years ago. But yeah. And then figuring out how physics works, oh, that's a huge pain. Go and see what other people have done so that you don't have to go through the pain and suffering of doing all that. Fun! Yes. So what were we doing here? Oh, right. Okay, so we're orienting the vectors there, and that influences the global transforms, but it doesn't seem like that's doing anything. Why would that be? Is that because I'm updating all of them right now, and they shouldn't really be doing that right now? But would it be different? Because I did factor out all that, and that should be completely fine. We should be able to copy this. And put you inside of here. And then that would update that, but no, we don't want to do that. And here, yeah, we don't need that part anymore. That part should be just fine. Replacing that with that, because that was already doing that, but no. Oh, right, the rotation has to be the original. No. Okay, we'll ignore that for now. Let's go and reopen the file. I'll need to do that when I have brain cells, which right now I do not have. Open recent, yada yada. There we go. We're back to where we should be. There we go. So now it's working again. Nice. Yeah, this gives us the... Again, we basically do physics on a point that's moving around. And actually, let me attach the actual visualizer for that. So here we have a ton of points moving around, and then that point becomes the new Z orientation of the bone. I could do another one for the normal, but I found that, you know, it could just use what it already had, and it works out pretty good. I haven't really seen any extreme snapping from that. Yeah, it's working out pretty good. Pretty good. Okay, let me read the chat again. Yeah, for any of this, to really click, it'll take practice. Tell me and I forget, show me and I remember, involve me and I understand. Yeah, you have to play around with it to get a feel for it. And then every time you interact with it again, you might forget something, so just keep playing around with it. You should make a bubble sim which also bursts on touch. I've already done that actually. A long time ago. That was pretty fun. Let's see. There's a whole new destructive tool selection to GeoNodes. Oh, right. Yeah. It's been a while since I've used that. But they can be very useful. GeoNodes tools, like, I'm all for that. I've been trapped into keep every single thing procedural that's possible. That's future me's problems. Yep. Let's see, the walkthrough. I appreciate the walkthrough of the functions. Yeah, I hope it can be helpful. Again, that's what I currently remember with my sleep-deprived brain, but I recommend actually looking up what they actually do, and it should be okay. Yep. Okay, I think I should wrap up the stream now, because I think I've gone over everything that I should. Like this thing, it does what it does. You've seen the blueprints, you can recreate the building from the blueprints. Okay. For me, material shaders helped a lot learning geonodes, but still the fear of geonodes is something you'll have to work with in mind. Yeah, because geometry nodes now are pretty similar to shader nodes, in the sense that they have the vector math nodes, and math is math. If you take the vector math, it will do the same thing in shader nodes, geometry nodes, and every other thing in the universe. Where geonodes starts to get more complicated is because the way it just applies that data is different than a shader editor. Because you have geometry, which in the shader editor, you don't have a line of geometry that you're dealing with just because there's just one shader that you're dealing with. You're not dealing with multiple shaders and doing multiple things to them. If that were the case, then this line would be red for a material, or for a shader or material. Those things are kind of different. Never mind. But this is because you can work on multiple pieces of geometry at the same time. And all that is good. And then when you're dealing with simulations like this, this would be similar if it were in the shader editor. The repeat zones are coming to the shader editor. We're just not sure when. So they are similar. So a lot of the knowledge transfers over. Just in geometry nodes, it's more advanced because, well, it needs to do more. Like 4x4 matrices technically do exist in our worked on, or they do exist in the shader editor, but they're just not exposed. That's more of an under the hood thing. Then booleans, integers, those are still geonode specific. Are quaternions? I don't think quaternions are in the shader editor. Are they even used under the hood? Or is that just the 3x3 matrix? I'm not sure. Because rotations in this rotation socket is a quaternion, but it can be, with this part, it's a 3x3 matrix, but you just separate the rotation component. And all that's fine. And then, yeah. But yeah, the shader editor is very helpful because it just, you don't have to worry about sampling indices and all that. While in here, you do have to worry about that. And all that is, it gets more complex in GeoNodes. Because with the shader editor, you just deal with pixels. While here, you have to deal with points, which are kind of, they're kind of like pixels. But then you have your edges, your faces, your face corners, which face corners are vertices in Houdini, which is very fun. Yeah, it gets so much more complicated than the standards breakdown. It's fun. But it can work. And then, I haven't done a lot of this, but my friends have done quite a bit in compute shaders, which in compute shaders, especially on stuff like Shader Toy, you can basically you have the ultimate power. You can do so much. Well, actually, wait, can you do that in Shader Toy? I think you can do particle-based stuff in Shader Toy, but I'm actually not all too sure. My memory is only showing me Houdini stuff in Godot. I'll need a refresh on that. But Shader Toy, you can do so much more than what you can in Blender just because it's more advanced. And in that situation, you get to see the parallels between, you know, editing geometry and editing pixels. And sometimes the two intersect, which is always fun. You can do a lot of cool stuff with that. Yep, there are entire games based off of stuff like that. Okay. Yeah, that is pretty much everything for today. Thank you all for watching. I hope you all enjoyed. Again, this project, it's more of a proof of concept rather than something that's practical, even though you can deform geometry using this. So, who knows? Maybe I'll be able to make it into something worthwhile. Maybe. We'll see. Thank you all for watching, and I will see you next time. Have a good one.